Yes.
Okay. Thank you for inviting me. It's really a pleasure to be here with so many students interested in the field in which I'm working. And today, what I'm going to present is an overview of my vision and my research activity in the field of machine deep learning and technology. And at the end, I will also present some specific activities for thesis which are available within my research group. Let me share. Okay, can you see the shared screen? Okay, great. Thanks. Thank you for the feedback. I would like to start this short talk by relying on a provocative question, which is associated to a news which appeared, let me say, in the mass market, associated to a smart toothbrush. What I would like to ask, I mean, myself and yourselves, ourselves, is how much smart must a toothbrush be before you can call him smart, which resounds in old songs, which could help us in formalizing the problem. From our perspective, the news was associated to a smart toothbrush that apparently was provided with intelligent functionalities. And here the comments raised by this very popular Italian newspaper was, okay, it is true that this toothbrush is endowed with some form of intelligence, but the question is, do we need it? And the second question, which is not here present, but is, let me say, the goal of my research is, where is this intelligence? Is the toothbrush, which is endowed with intelligence, so the intelligent processing is done locally, or the toothbrush is just a collector of information and everything is sent somewhere, probably to the cloud, where the processing is then carried out? So the question is the toothbrush intelligent? And the next question is, where is this intelligence? So this is somehow the goal and the vision which I will try to explore during this short talk. In particular, my expertise, my background is in the field of hardware. So I come from the hardware research group, and in particular, our expertise is in the design of embedded system, wireless embedded system, so something which is work in the environment. In addition, I do work in the field of data center because I do have I'm the lecturer of the course of computing infrastructure. And so from the technological point of view, the two relevant, let me say, technological trends that nowadays we have refers to IoT and edge computing. And these are popular topics, and obviously large-scale data center. On the other hand, we have machine deep learning, which are the techniques that allows to, I mean, you are here, so there is no reason to say much worse than they are crucial for what's going on in the next future. But in particular, my specific research activities is the combination of technology and machine deep learning, where on one hand, we want to take machine deep learning and we want to move algorithms to the new technological solution, which could be, as I said, either IoT solutions, so heavily constrained in memory, computation, and energy, or large-scale data center. These new technologies are cloud computing platform, or if we move to the so-called X learning as a service, all the machine learning as a service, deep learning as a service, forecasting as a service. So we change the paradigm of the machine deep learning to be tailored to the data center and to the large-scale computing. On the other way around, when we move these units, these devices, these technological solutions in the real world, we have to take this into account in our algorithm. Let me say the most relevant one, for example, is the fact that all the machine and deep learning algorithms rely on the independent and identically distributed hypothesis, meaning that data are stationary over time. But this is not true in real world situations, because the environment changes, the world changes, the users' behaviors change. And this means that we need to adapt our machine deep learning mechanism over time. This is also true when we take into consideration that when we move these devices in the real world, we might have faults. We might have faults in the actuators, in the sensors, in the hardware. We might have changes in the environment. We might have, I don't know, all the types of effects associated to seasonality, periodicity, market changes, which must be taken into account while designing our machine deep learning. Let me show you a couple of examples. This is a scenario where we move let me say, an intelligent and smart IoT devices aiming at forecasting the rock collapse. Here you see MEMS accelerometer, which are within this case. Here you see strain gauges, which are measuring the enlargement of macro fractures. And this is the, let me say, the beautiful Como Lake. This is the San Martin Mountain. This is the town of 𝗏𝗏𝗏𝗏𝗏. Why do we need intelligence on the mountain? We need intelligence because we cannot transmit everything to the cloud or to a remote computing center for the processing. Processing must be taken locally. But if I have to take a decision locally, for example, raise an alarm, I must be able to distinguish between a true enlargement of a fracture or the fact that the strain gauge, which is a metallic pipe, suffers from the heat. So it enlarges during the day and it shrinks during the night. If I'm not able to decouple the fact that it is a true fracture or it is the effect of something else, I'm not able to be effective in identifying dangerous situation. So when we move something to the real world, these devices, these smart systems must be endowed with some form of intelligence. This is the same in the scenario of the monitoring of a data center, where here the monitoring is associated to whether vibrations of the rack or identification of area within data centers which are, let me say, colder or let me say warmer, and this allows to have a better balance of all the cooling infrastructure. This is an example where when you move something to the field, this something must be endowed with some form of intelligence. But the same holds, for example, when you have to make forecasting of say, everything. Here we have the forecasting of the prediction for the COVID. We might have forecasting in the selling of some goods, or forecasting the number of tweets that are associated to a specific topic over time. If you want to make a prediction, you have to create prediction model, but these prediction models must consider the fact that it is mandatory to take into account the fact that time passes and there is an evolution over time. So, for example, if you had a prediction model for the correct forecasting of what you are going to sell or the interest of the user before and after February 2020, for sure your prediction model quickly became obsolete. And this is due to the fact that something changed and you have to adapt your model over time. These are some of the companies with which we have collaborations in order to also work in the field of thesis. This is the starting point of this short talk, which is associated to the fact that often when you talk about AI or machine learning, you think about algorithms. But here you have a definition of AI. It is in Italian. I will translate it in English. So AI is the area of computer science meant to study the development of systems comprising hardware and software endowed with abilities which are typically associated to human beings. So we have hardware and software, and this is exactly the goal of the research in the field of AI. You have to design hardware, so new technology, and software, new solutions, new algorithms. Hardware and software, you are computer science students, so you know that when we talk about AI hardware, means all the hardware resources that we can rely on to run our algorithms. When we have software, we know that we have a platform, let's say environment software, in particular the operating systems, or the application, which is the reason why a system exists. From this perspective, it is interesting to see that differently from traditional computing systems in the hardware for AI, we have, I would say, state-of-the-art solution, data center, edge computing, IoT, but we have also hardware accelerator, which are mathematical processors meant to execute in a fast and effective way specific instructions associated to the machine deep learning. And then we have the application. What is the application? The application is the reason why a system exists. It could be an application meant to distinguish between cats and dogs, or it could be an application meant to distinguish while I'm running if the, let's say, vibrations of my smart sensor is associated to a normal case or to a normal situation. This is the application that we can have. When you say, hey Google, or hey Siri, that's the application of detecting a specific tag in what you're saying. That's the application. And in the middle, you have all the platform, which are the toolbox, the frameworks, and the libraries which are available in order to, exploit the AI hardware. So exploit as much as possible the hardware resources and design new application. And this is exactly the framework that we typically know when we are talking about computing systems. So we have the hardware, we have the operating system, and then we have the application. As regards the hardware, we have, as I mentioned, different ranges of families from the small IoT devices going up to the data center. Obviously, here we have different performance, power consumption, say memory abilities. Let's start with the data center. Considering that apart from IoT, I might have all the hardware coprocessors and all the hardware accelerators that support in an effective and efficient way the computation of machine deep learning. Let's say a few words about data center, where here the hardware is obviously nomen omen the data center. Here the AI platform refers to the cloud and all the machine learning and deep learning solutions that are available on the cloud. And the application is the machine learning and deep learning as a service. Let's try to make some concrete examples, some tangible example, just to say what I'm talking about, referring to platform and application. Here we have all the words which are associated to the as a service something. Today, as a service is a very popular approach in the field of the data center and the field of cloud computing. If I'm talking about infrastructure as a service, here I have all the infrastructure that I can find on all the cloud providers, EC2, the Amazon, the Google Cloud, Azure Deep Learning. And here I have to design from scratch to say the software, the AI solution, and also I have to select the hardware. If I scale up in the field of platform as a service, I do not care about the infrastructure. So I'm not required to create a virtual machine or a container. I'm using a platform that has embedded the container and the associated virtual machine. But I use it, for example, SageMaker, CloudML of Google, ML service of Azure of Microsoft. And here I have just to design my AI solution. Going up, I have ready-to-use solutions that rely on machine deep learning. One very popular example is Recognition. Recognition is a service which is provided by Amazon. You can call it through a REST infrastructure. You send an image and then you receive back on the image all the objects which are present. You received again in JSON formats the class that you find, I don't know, a person or a bike or a dog or everything. together with a confidence. This is in as a service, a solution as a service, because you are not required to design or to develop anything, but obviously you have a cost to pay. So for each call of this API, you have to pay something. But this is the solution as a service approach. Which are the advantages and disadvantages? The advantages are associated to the fact that cloud computing obviously simplify the access, because you can design a solution without having a deep knowledge of machine deep learning. If you are an SME, you want to quick and dirty. You want to something which is working. You are not an expert, but you want something which focus on your specific problem. The second advantage of this cloud computing approach is that you can easily move something from the prototype to the production, the so-called ML ops. And in this case, you can just open the virtual machine or the container that you designed to the open world. But obviously, you have also to pay something because there are no freelancers. Having everything on the cloud, as I mentioned at the beginning with the smart toothbrush, requires a permanent internet connection. Do we have an internet connection to all the objects which are close to us? And often this is an approach which induces a very high power consumption, very, very high. The power consumption of the data center will be a problem in the next 3 to 5 years. And then we have obviously problems associated to the privacy and security. In particular, I'm focusing on privacy because when you move something to the cloud, because you want to, as I mentioned, you want to use the recognition functionalities which is provided by Amazon, you are sending your image in a plane. So it is free of use. Do we do the same approach with sensible data, something which is associated to medical information, personal information, I don't know, economic information? Do we want to send everything in plain text to the cloud for the processing? I will answer this question later on. And last but not least, the latency with which we make a decision. Because if I move everything to the cloud, I have, and in the middle, I have the internet connection, I have all the processing which is associated to the different steps, but I cannot set real-time constraints on the processing. And so, if we want to deal with this problem, we have to move to a different approach, where the AI hardware is not just a data center, but it is everything I can move pervasively in the environment: IoT devices, embedded personal computer, edge computing system. Edge computing, which I'm sure you know that the 5G networking will be endowed with edge computing units supporting the pervasive computation close to where the data are generated. Why? Because the goal is to move the processing, and in particular the intelligent processing, as close as possible to where the data are generated. And we have also some interesting platform for IoT devices and embedded PC, like for example TensorFlow Lite, PyTorch quantization. We have the 𝗙𝗀𝘽𝘎𝑙, which are all platforms and techniques that allow to design machine learning algorithms able to take into account the constraints that we have on these pervasive devices. And thanks to this approach, we can increase the autonomy of our devices because the decision can be taken locally. We can reduce the latency with which we make a decision, because if I have to raise an alarm, the device itself can say, oh, this is a normal situation, or your heart is bumping in a non-correct way. And I can do that even if I do not have a connection with the smartphone or with a connection with the cloud. I can reduce the transmission bandwidth, and this allows also to reduce the energy consumption, because as you know, the transmission is the most energy hungry activities within an IoT devices. And if I can process data locally, I have much less problem in security and privacy. Obviously, the two approaches, so machine deep learning as a service and machine and deep learning platform for IoT and edge, which are both we say sides of my research activities, are not two contrasting solutions, because at the end we will have solutions where both approach will be merged. where we will have machine deep learning solutions managed as a service when we have enough, obviously, power consumption, internet connection, but the rest is then moved to all the scenarios where we want to delocalize the processing, where we want the so-called embedded and edge AI, where the edge AI is perfectly distributed within the network of different devices. This is my point of view, but this is also emphasized by the very interesting news which appeared in the IEEE Spectrum, which is the magazine of the IEEE, saying that let me say the skills that are more requested by the employers' wish list, so those who are, let me say, hiring people. And here there is the difference between the same topic in 2014 and in 2019. As we can see, the topics which gain the most relevant increase are machine learning, where we have an increase of 439%. In Python, 123%. And then all the, let me say, topics are associated to the cloud-based machine learning. So AWS, 418%, Azure, 1000%, and Docker, so container, 4000%. This is an increase in the interest in the skills which are requested by computer science and computer engineering. Okay, let me go to the topics that are available for thesis. I will here describe 3 different topics of thesis. The first, obviously, is the field of embedded and edge AI, where the goal here is to move the intelligent processing, and more specifically, not just the processing, but also not just the inference, but also the learning to the embedded and edge devices. So the idea is to rethink the algorithms that we know, the recurrent neural networks, the convolutional neural networks, also all the machine and deep learning algorithms, in a scenario where we have significant constraints on the memory, computation, and energy. And we can do that by redesigning from scratch these solutions, tailoring to the constraints that we have in these technological solutions. And if you think about all the technological objects that you have either in front of you or in your room or in your house, and if you imagine that all these devices could be endowed with intelligent functionalities, you can quickly imagine how relevant is this research field. By also considering that in addition to a single IoT devices, you might have that a machine deep learning solution could be spread out on an ecosystem of devices, hence allowing the processing, the distributed processing in an ecosystem of technological units, which could be also heterogeneous. For example, you might have a complex convolutional neural network, which is ported to a set of Arduino devices together with some Raspberry Pi devices, which are able to process the most computationally intensive layers. And here the topics are tiny machine learning, federated learning, learning in stationary environments, and zero-shot learning. The second field refers to the privacy-preserving machine deep learning. This is a research area that I really support because allows the design of machine deep learning which are able to process encrypted data. It is a very novel research area where the goal is that you, as user, encrypt your data, and you rely on machine learnings that are able to process encrypted data, and then the results of this processing is still encrypted, and you as user can decrypt and have the correct evaluation. And think about all the machine deep learning solutions which are available as a service, and instead of receiving data, plain data, you can send them encrypted data. So our goal as designer is to design solutions which can be used as a service, or more generally, which can be used as algorithms which are able to process encrypted data. So here we have encrypted learning, approximate computing, AutoML for the tuning of these algorithms, and all the field of machine and deep learning as a service. Last but not least is associated to the deep learning as a service for time structured data. What I'm doing within my research group is the development of a platform which is now available in GitHub as open source for the processing of time structured data as a service. So we receive some inputs, and then we process the inputs, and we build the whole pipeline for fitting data, which can then be used as a service by non-expert users. And we applied this to the forecasting of, I don't know, the usage of particular services for the selling of goods, but we applied this also for the forecasting of the COVID, having very, very interesting results in how the distribution is propagated and how different KPIs, so different figures of merits are related to each other. Okay, I think that I'm done. I'm more than happy to answer questions, if any, or otherwise, here you can find all the links to contact me now or later on, and I will be happy to answer all your questions.
Okay, thank you so much, Professor. I'm not seeing.
Okay, I think that you can.
That's a question.
Okay, I'm receiving a question about prerequisites. I would say no, in the sense that I strongly encourage students to start their thesis when the number of remaining exams is not too high. Or not too high, I would suggest 2 or 3 most. If you have 5 exams which are remaining, I strongly encourage students to complete their exams and then starting their thesis, because otherwise you might fall in love with a specific topic of your thesis, but you still have to go back to the exams, which could be either, I would say, easy or hard, and that might be, let's say, an unpleasant situation when you have the thesis which is completed and you still have 5 or 4 exams to fulfill. Did I answer your question, Francesco? As regards to the topics, no specific prerequisites is one. I would say that the topics which in which you are not strong enough, we will help you in, let's say, feeling and creating a background which is solid enough to fulfill all the goals of your thesis. Okay, so you might require an initial overhead, I don't know, to fulfill or to increase your knowledge on Python or machine learning, on time series analysis, if you're interested in, and that's this is what you want to do as thesis, you can quickly go back and having all the information which is necessary to complete the thesis. How is the job market for privacy research in machine learning? There is a strong interest on this for the creation of solutions, machine learning solutions, which are able to support the execution of privacy-preserving machine learning algorithms. And this is for all the cloud providers and for all the SME and big companies that provides solutions, machine learning solution as a service. You're welcome. Okay, it was a pleasure for me to be here. It was a pleasure to meet you and enjoy the rest of the event, which is really worth. Ciao, Mark. Okay, let me just add one word about this, because the topic, which is related to the privacy preserving machine learning, I'm exploring different areas of machine learning, and one of these different areas is in collaboration with Professor Mark Carman in the field of text analysis. So what we are doing is the design of privacy preserving machine learning for the text analysis and classification. And then I leave you the stage, Mark.
Okay, thank you.
That is an awesome project. So anybody who's interested in doing really cool, really high-end stuff should seriously consider that one.
Okay, so if this is it, thank you so much, Professor Roveri, and we can move on with Professor Carman.
Perfect. Hello, everybody. Thank you, Manuel. That's, as I said, a really, really cool project. In general, all of the projects in data science and Politecnico are going to be a lot of fun. So you guys get your pick of interesting projects to work on, which is fantastic. Just before I start, how long do I have to talk?
Half an hour.
Oh, wow. Okay. Nobody should ever give me half an hour. I start talking and don't stop. No, hopefully it'll be interesting for everybody. Okay, so I prepared a few slides, but mainly what I'm actually going to show you is a bunch of demos in a minute to try and give a bit of a feeling for the work that I do and the thesis projects that are on offer, and I have been, or the thesis projects that I've been supervising recently, which a lot of the ideas will just be extensions of them. And a lot of the projects are in collaboration with other professors at the Politecnico, Manuel, and with 𝗙𝗀𝗽𝗎𝗪𝗍, and possibly Professor Boracchi, etc. So let me share my screen with you all. Hopefully you should see a PDF, not PDF, PowerPoint with just some thesis proposals. Oh, that date obviously isn't correct. Okay, so can everybody hear me okay? Somebody say yes.
Yes, we can hear you.
Okay, perfect. Okay, so for those of you who haven't heard who I am, I'm Australian who teaches at the Politecnico. I teach data science related subjects and text mining related subjects, but not generally to computer science students. I'm teaching either to cybersecurity or to mobility students. So many of you wouldn't have seen me in the classroom, but I'm into data science. That's what I teach, and it's particularly into deep learning. My background is in information retrieval, so web search, so all text mining and natural language processing. In particular, recently I've been ever more interested in bioinformatics related activities as well. Okay. And so the types of topics that I look at are analyzing social media. There's some work together with 𝗤𝗙𝗎𝗄𝗎 on that. Automated fact checking. 𝗙𝗎𝗙𝗎𝗢𝗎 was involved in that for a while as well. Digital forensics, together with a researcher from telecommunications. And genomics related research as well, with various people from Stefano Cerri through to Marco Massaroli. Okay, so lots of different collaborations with other people. Thesis projects that I'm interested to supervise, and I'll run through specific ones in a second, but in general, they're either going to be deep learning applied to problems in text, chatbots or text classification, etc., or deep learning with images, in visual question answering systems, and the like. Deep learning with genomic data, that can be protein sequences. I'm very excited to try and get a student to continue work that a previous student has been doing there, and I'll try and show you a demo in a minute. And more recently, I've had a lot of contact with different companies and also with people in mechanical engineering, because I teach students over there as well. And so I'm interested in deep learning applied to problems with transportation data. So I'll show you an example in a minute. So lots of deep learning if you're into deep learning. Going a bit deeper into these topics, one of the demos I'll show you in a minute is all about fake news detection, or in particular, it's about helping journalists to detect false claims in text. So we're trying to build a system, and had a couple of students in the past who've done theses in this area, and we've developed a nice system to try to help journalists fact check that statements made by politicians. I'll show you that in a second. I've also been supervising a student looking at drug repurposing. Obviously, COVID is a massive phenomenon, and so everybody was a bit interested in whether they could help out in COVID-related activities. And one thing that we were looking at, although not specifically for COVID, is whether for a particular virus we can determine which drugs might be useful might likely interact with the proteins that that particular virus produces. So I'll talk more about that in a second. I've had a couple of students now working in the area of digital forensics, in particular looking at deep fakes. So these are videos that have been doctored in some way. They're not real videos. Again, I'll show you a demo in a second. And there's an arms race at the moment to try and develop detection systems for these videos, because they could be used for all sorts of terrible purposes, from influencing public opinion to online harassment. They're very, very commonly used in bullying situations, and so we need to be able to detect them. Also, in order to protect the use of video as evidence in a court of law, we need to be able to determine whether the video has been doctored at some point. And so so there are a lot of classifiers that look at that problem. We were trying to look at building explanations for why why the system believes that a video might have been doctored. I'll show you that in a second again. It's a general theme through the work that I'm doing that I'm very much interested, more than just in building machine learning tools for making predictions. I'm interested in building tools for explaining the predictions of the models, so that the machine learning tools are useful in practice to somebody for whatever purpose that they've been built for. Lots of work in extracting useful information from images and building pipelines from social media. I'll show you an example of that in a second. This is particularly interesting also for police investigations. So sometimes police come across images of crime scenes, and they'd like to prosecute, investigate, protect the victim in these situations, but they don't actually even know where the image was taken. So we done some work in that area too. And then very interesting at the moment with images is all of the convergence of medical diagnoses and systems for helping medical professionals make diagnoses. And so there's a lot of really interesting data out there at the moment, and I'm going to again talk about that a bit more in a second. These are some very rough slides I put together in the last 2 hours before, or hour before this presentation. So we'll see how some of them are a bit more polished than others. Here's one polished slide, which is talking about a project. This is actually, we're requesting a PhD 𝗙𝗢𝗟𝗪𝗪 for this project. Whether or not we'll get it, it remains to be seen. But the project is about making use of deep learning together with for infrastructure monitoring. So the idea is all around Italy, or in fact all around the world, the infrastructure maintenance or the infrastructure providers. So in the case of Italy, it's RFI. Those that are providing the transportation railway infrastructure need to monitor that infrastructure to determine whether or not there are issues along the railway lines. Usually this is the geometry of the railway line they're interested in. If that geometry gets, if the lateral or vertical displacement of the tracks comes goes beyond certain tolerance, then they need to intervene and fix the tracks. And the way that they determine whether or not, they determine that geometry is they run around periodically over all of the railway lines. In this case, in Italy, there's a special train called 𝗖𝗎𝗎𝗄, which runs over all of the tracks, primarily the high-speed rail tracks, but also some of the slower rail, and it measures the track with some sort of measuring equipment. Now, the idea with this particular project that we want to start as a master's project and then hopefully continue towards a PhD is actually to make use of all the trains that are out there, all the fleet trains that are traveling over the tracks continually. They happen to have in them all sorts of instrumentation, not designed for measuring the geometry of the track, but actually designed just for determining the wear and tear on the vehicle. So lots of gyroscopes and accelerometers sitting just above the rolling stock in the wagon, and we'd like to try to make use of that, the signals from this from these accelerometers, together with some deep learning, train models to actually monitor in real time or closer to real time the geometry of the rail. Obviously, we need this deep learning in this case because we can't make use directly of these measurements from the trains. These measurements are not don't have the fidelity of the diagnostic vehicle measurements that Trenitalia or Ferrovie dello Stato would normally be collecting. So there's a project here to see whether we can take the data from the trains, the ground truth from the diagnostic vehicle, and some deep learning to try and actually do closer to real-time monitoring of the geometry of the rail. Okay, that's one project in mobility related topics. Another project I've just recently finished with a master's student, Virginia Negri, did a fantastic thesis looking at indoor geolocation of images. So this is a problem that's motivated by the police. They sometimes come across images of crime scenes, as I said, and they'd like to know where the image was taken so that they can intervene, look after the victim, prevent further crimes, and obviously quite horrible crimes from being committed. So in Virginia's work, we looked at trying to build classifiers automatically from images, from indoor images. Usually we do this with outdoor images, although even with outdoor images, the quality of the geolocation, content-based geolocation isn't fantastic. With indoor images, it's a really challenging problem, but there are lots of signals in these images. So in this particular image, we can see it's probably a picture of a hotel room. Maybe it's in Florence or Rome. And in her thesis, what we looked at also was taking saliency maps over the images. To improve performance of this classifier, we actually placed a tension over the image. We used object detectors over the image too in order to, and then text generation software to try to explain what features of this image might be responsible for the prediction. Now, what's the idea here? Well, if we wanted to convince a police officer that this picture was taken in Italy, we'd have to tell them, well, these plugs are very common in Italian hotel rooms, etc. Okay, now I'm running out of time, so I better really be quick. Another area that I'm really interested in looking into is building chatbots, in particular chatbots for explaining the predictions of a diagnosis system. So imagine a conversation between a doctor and a chatbot saying, you know, why is there an elevated risk of coronary heart disease? This is a diagnosis. Well, the bot is saying because the patient's blood pressure was high and she has high to medium value of low density lipoprotein. No. And then there's a discussion back and forth explaining why this diagnosis is correct and what would change if the patient presented slightly differently. So it's a project I'm interested in. Another related project, building chatbots. We've had discussions with Pietro Pinoli about building a chatbot for helping develop helping scientists do genomic data analysis. So they're usually trying to discover what genes are related to the severity, what genes indicate severity of a particular disease or increase its propensity to occur, what mutations are related to a certain pathology, etc. And so a chatbot helping to determine what this task is and a workflow to provide for that kind of analysis is where we're heading. Now, this sounds quite complicated and is kind of a complicated problem, but we're going to start building a chatbot to help with that sort of analysis. Social sensing, I discussed very briefly. We're building a pipeline, or we have a pipeline. This is an interface that we're trying to develop for it, which starts off with keywords in Twitter, in this particular case, or some other data source, gets all the images back, and then starts filtering those images based on a number of deep learning classifiers to try to identify only the set of images that are useful for the particular task that the user is interested in. Maybe these, in this case, these are pictures of rubble from the recent Albanian earthquake. And how have we found them? Well, we've filtered on location, we filtered on the type, it's an outdoor image, that there was rubble, etc. Okay, I'm taking more time than I wanted to with these slides, so I'm going to pop across. Here's a bunch of examples very quickly of the type of research that I've been doing recently, and in particular the projects that I'd like to move forward with. This is the fastidicity, so fact-checking system. Oops. That was developed by Stefano Agresti. The idea here is we might take a particular speech. This is, or a text by a journalist might take a text by a particular politician. This is a speech by Donald Trump to the United Nations. And then the system analyzes that text. It looks at every statement in the text and says whether it believes that that statement might be making a claim that could be fact-checked and might be worth fact-checking. So a statement like America's economy is booming like never before, or since my election, we've added 10 trillion in wealth. These are statements that could be validated, could be checked by a journalist to see whether they're actually true or not. As you can imagine, Donald Trump made a lot of statements that didn't actually turn out to be true. This system, what does it do? It checks whether the text overall appears to be biased, if it's leaning to the left, political left or right, if it seems to be written by a professional. And then we can take statements from the text, we'll do some analysis on them, and we can search online for articles in the news that might be supporting or refuting that particular statement. So this particular statement was, since my election, we've added 10 trillion in wealth. Okay, and so we'd find articles that may may support or refute that particular statement. And so that would help a journalist who's then doing their analysis. And so I'd like to move forward with this, improve the quality of the classifiers, as well as overall make the system, but perhaps actually do a user study with real journalists, which would be a lot of fun. I'm going to show you a couple of other things very quickly. Here is a system for data integration that's based on analysis of text. The idea here is to help those scientists who are attempting to answer the question, you know, which gene is most likely causing or having a causal influence on a certain type of breast cancer, let's just say. We have there is a system under development called GenoSurf. At the Politecnico, this is a system which allows for structured search for all data sets online, which talk about a particular type of which contain genomic data related to a particular disease. So if imagine we could look at kidney carcinoma of the kidney, we could try to find all individuals of a certain, say, all samples of a certain gender. Obviously, we're after humans in this case, and eventually we can get to all of the data sets that are out there and aggregate all of the data so that we can then do our analysis on that data to try and determine whether a particular gene, say, has an influence on survival rate, perhaps, for this particular type of cancer. Why is this important to be able to do? Well, whenever people are doing this sort of medical analysis, they can never find they never have enough data. The more data they can find online, the more data that they can find, the more likely they are to be able to come to a useful conclusion. So this system, Genomic Data Integration System, which was developed by a pair of students in two theses. 𝗙𝗎𝘎𝗎𝗀𝗎𝗓 built the interface now that's being used, which is fantastic. This is actually a system that produces the back-end data for this, or is planned to produce the back-end data for this GenoSurf web search system. Now you can see here we've got lots of structured data. The problem is online, when people upload their actual data, they describe it in natural language. So oh goodness, let's see, something's wrong. We're missing some fields there. Anyway, it's fine. And this system is a data integration system which looks at a particular, looks at the textual data and is trained to extract the appropriate fields from that textual data. Now, for some reason I can't show you with many fields, but generally we have lots of fields we're extracting, and we can see when we do extract that data, where in the input text the model, what part of the input text the model is used to determine the actual value for these different fields that it's extracting. Okay, so I'm not sure what I can show you. This one's a bit longer. There's only one there for some reason. And this is an active learning system, so the user sees the responses and then they can modify them. So here the system's not particularly confident about this being a sample of brain tissue. Maybe it wasn't. So the somebody who's editing, who's actually making use of the system, can change it to be change the biosample term name to be whatever it is. Maybe it's kidney. Okay, so that's one system that we're developing at the moment. And I really wanted to show you that because I wanted to show you a drug repurposing tool, which I'd like to extend. So this is a different project that was the interface and system was developed by Simone Lancellotta, a previous master's student who's just graduated. The idea of this system is we're going to take a protein sequence. So let's have a look quickly at a protein sequence in CBI. So this is the this here is the COVID. This is genomic data related to COVID, and I can have a look at all of the protein sequences related to the COVID virus. Now, I don't really have a lot of time to talk about this, but basically the virus is a DNA sequence or an RNA sequence. It moves around, it gets in your cells. The cell is like a printer. It prints out copies of that virus. It also, at the same time, prints out proteins based on the RNA sequence in the virus. And so let's just grab a protein. Let's have a look at one. There's a very important protein called the spike protein. That's the one, as far as I know, that the current that the vaccines are based on. But I'm going to look at one protein. Here it is. I'm not sure. This is not the spike protein. It's a bit shorter, but it is another example of a protein. So you can see it's a text string made up, and each of these represent amino acids. So this is the language of proteins. If I now go back to our demo on drug discovery and I can put that protein in, fingers crossed, I haven't run this for a few days, this model, it's just updating. Over on the right here, what are we seeing? We're seeing, oh darn. Okay, we're not going to see, but I'm going to have to talk to you through what should have happened if I think we might have too many demos running on the GPU at the same time here. Might be a memory issue. Anyway, over here on the right, we have a representation of all the protein sequences in the embedding space that is produced by a particular model called BERT, which we have trained on these sequences, on sequences of proteins. The colors here represent the different families of the corresponding viruses that are producing these proteins. Okay, and so what we should have seen here was where this particular protein sequence for the COVID virus, we should have hopefully seen it pop up amongst the coronavirus. And then we should also have seen the classifier come back and say, well, this is a protein that we believe comes from the coronavirus, and this is the set of drugs that we think may possibly interact with that protein sequence. How do we train that? Well, we have a lot of sequences. We have past information on drugs that interact with certain protein sequences, and so we're training the model to recognize parts of this sequence that it might interact with. So I'm almost out of time. If you probably am out of time, but I have a number of other demos that I'd love to show you all, but I don't think I can. Even my family seem to be after me. This I'm just going to show you very quickly an example of. Sorry, I'm just going to cut that. Okay, here is an example of the work we're doing with deepfakes. So we can look at a particular video here. And the question here is this has this video been doctored in any way? I'm going to go with no, it hasn't. It's a real video. And the answer is yes, it has. It's a fake video. The face has been changed on this video. And then we have different explainers that we've developed to have a look at individual frames to explain what is it that may have caused the classifier to determine what part of the frame is it that's to cause the classifier to determine that the video has been edited in some way. Okay, and the last demo, so there's one more demo on the deepfake related stuff. What have I not shown you? Oh, and then I have a visual question answering demo that was developed by Alberto Bellini, working with 𝗙𝗢𝗎𝗎𝗪 and myself, which is a lot of fun. This is a question answering system related to images, so we can ask what is that animal, for instance, and hopefully the system will tell us it's a dog, and it will actually show us where it's looking in the image as it's passing the question on the input and as it's producing the answer on the output. And so there's ongoing work with building better systems for doing visual question answering, and also in the medical domain. Okay, so I think I'm probably out of time. So I don't want to eat into somebody else's time.
No, Mark, it's me. It's not a problem. You can
it's only Giacomo. Ah, well then, hold on. I've got another 20 minutes. Wait no, I'm kidding. Giacomo does fantastically interesting projects. And we've been planning on doing projects together for a long time. And we are actually, one on explainability at the moment, which is great.
We are. And even if there are no like explicit slide on a collaboration, it's like collaborations can spark. If you
exactly. So that was a point that I was with any of us. I mean, we have projects that we plan to do, but if you have really interesting ideas that you would like to pursue in the area of one of the projects or the area of interest of one of the professors, talk to them. Definitely Giacomo and I would like to supervise some interesting projects in the overlap of our interests. So, okay.
They're also office mate. So
we're all yes.
Once when we used to go to the office,
we used to see each other regularly. Okay, so I will. I'll stop sharing because, as I said, I won't want to run into Giacomo's time. If anybody had any very, very, very quick questions for me, they can otherwise email me. Yeah. Any questions? Does he always talk this fast? Yes. When I only have half an hour to talk, I always talk this fast.
You get used to that.
Yeah, it's a way.
Just people a matter of the beginning.
Have a teletext thing. Do you mind if I record you so I can understand what you said afterwards? Yeah, that's fine. Thank you to the organisers for organising this. They're always great for us as the professors, or I love them because it's a great chance to talk to students who are interested in this area.
Thank you so much, Professor, for being here and for giving your presentation.
Thanks for organising it, guys. I'll leave you in the capable hands of Giacomo.
Thanks, Mark. Thanks.
See ya.
Let me start sharing the presentation. Can you see my screen?
Yes.
Okay. So, let me. So these are the slides that you can find also on my website, where you can find maybe more opportunities. So I will be rather focused on thesis proposals, and I'll give you just a brief overview over the topics we are working on. And these concerns, say, image processing, and now you cannot, do image processing without an eye over deep learning, so it's both topics. Then there is something more related to computer vision, so inferring the 3D structure of the world from images. And now today I'm not going to talk about conventional imaging modalities. I'm just talking about like so this is like mostly related to images on this side. On the other side, there is something that is more related to machine learning, and whether we talk about it's our studies on machine learning for health, and in particular those related to machine learning for studying nasal pathologies, analyzing the CFD, computational fluid dynamic simulations, and at the end we talk about something that is maybe most of interest for you, like is data scientists, that is anomaly detection over data streams, so data stream mining techniques. And yeah, as I mentioned before, I'll give you just also a background and a few research directions where there are like theses. I'm not expecting you to understand clearly what you're going to do in a thesis after this 30 minutes presentation, so just drop me an email if you are more interested, and we can discuss together. Of course, I'm not the only one supervising this thesis. So these are my PhD students and one postdoc, Luca Magri, and a couple of friends and colleagues, Diego and Simone, one from ST Microelectronics and the other for 𝗙𝗢𝗎𝗍, which are helping me in the supervision of projects that are of common interest. Again, for each question, just drop me an email. So, and of course, ask the question after this presentation also. One of the major problems we are addressing in these days related to image processing or image analysis is anomaly detection, which means the detection, so designing algorithms that are able to detect regions in an image which do not conform to a well-defined notion of normality. So a well-defined notion of normality can be, for example, in these nanofiber images, so in these filament images which have been acquired by over a SEM microscope, the normal region are these filaments randomly placed, and where the anomalies are those stuff highlighted here, which are like the detection from our algorithms. But this can be also tumors in mammograms, defects in manufacturing, like the one you can see here, or in this very recent data set where you can see that there are a lot of anomalies annotated in these kind of images, which refers to small defects in these images. And yeah, these I already mentioned. This is the scenario where we started from a few years ago, collaborating with CNR over this data set, and we designed our anomaly detection algorithm, and we made the data set publicly available. And that's how we started working in anomaly detection. So now we kind of got, we are kind of satisfied of the work done over images, and we want to work they want to add a third dimension, so we want to work on point clouds. So now the idea is to localize like defects, or as you can see here, bumps over three-dimensional surfaces, where again, you can leverage as primitives, as prior information for establishing what is normal and what is not. Say the fact that locally there is some kind of smooth function describing the normal regions. Why for anomalies this doesn't hold. And so this is the first thesis. We are like looking for champions are that concern anomaly detection in images and point clouds, and these of course concern all the also deep learning models that can be used over point clouds that are like less popular than those for images, and also using like what is referred here as data-driven embedding techniques, which can be used to bring our observation into like what is called the vector domain, say in the latent space, where we can handle like our data to anomaly detection techniques that are from statistics. Okay, in most of the cases, I'm not mentioning everything in the slides, but typically we give access to a server mounting a GPU. This is not very needed nowadays because most of the students use Colab. But still, then for the model, once it is ready, and for the very most extensive and last say simulations, we can provide that. And also data set and everything is written where it is provided. And another scenario we want to perform anomaly detection is in a reference-based scenario, so where you're given an image which might contain anomaly, and an image which does not, which is the reference. And then, I mean, the comparison, the detection can be done, say, very straightforwardly by comparing the two. The problem is that most often the target image which you want to analyze and the reference image, which is anomaly-free, are from different modalities. I mean, this holds in medical domain where you got image from MRI or PET scan, or from, say, cameras where you got infrared RGB images, or in the domains we are mostly interested where you got data from an infrared, say, camera, like in this case. This is from our partner, an industrial partner we are collaborating with. You got an image of a big freezer, and you got the temperature recorded by the infrared camera, and you got, oh, sorry, the other way around. So this is the infrared, and this is the simulated temperature from the CFD, computational fluid dynamics. Now, you might understand that comparing the two images in order to understand whether there is something in your picture that refers to a region that is not that does not conform with the reference, which is like a simulated reference from, say, computational fluid dynamics, it's not straightforward. I mean, these are completely different inputs. So in this case, you have to also address like registration algorithms and intensity transformation algorithms to compare the two, and then decision rules that are far from being straightforward. I mean, there will be plenty of differences still after this. You compensate from geometric and photometric distortions. So besides anomaly detection, there is also, we are interested also in image restoration. Image restoration, like noise suppression, is kind of one of the primary problem in image restoration. As you can see here, you're given a noisy image. You want to provide as output a clean image, and you can find these algorithms, you say, in every device, in every device having a camera. And typically, the output of the sensor is like this. What you get from a picture is far from that. And there are algorithms everywhere in our phones that leverage some prior in your images in order to separate what is the noise from what is the clean image, what is like the smooth images as we are used to. And now the problem is how to design these priors. So of course there is like a big effort in these days from deep learning algorithms that are providing like the state of the art also in this domain nowadays. Yet these are the traditional algorithms are like way more efficient and still very effective. So what you get in your phone is one of these like algorithms based on still handcrafted priors. And one of the most effective priors is that in order to get rid of noise in an image, you have to gather similar patches, say small portions of the image that are very similar. As you can see here, this red block, it's called the reference, which is the one you want to clean. Then, of course, you will use the reference, you scan the reference to the whole image. And then you gather multiple of the other ones, like these blue ones, that are similar in the sense that they contain the same, the noise-free image is kind of the same there. If you gather these together, then you are able to suppress the noise very effectively. Now, what I'm going to do is to use different techniques to gather these similar blocks, similar patches, and while you can find efforts in deep learning models that are performing end-to-end denoising from, say, taking the noise image until the restored image, say the noise-free image. Now, what I want to do here is to just have a small model, data-driven model, that is estimating the distance between different patches. So instead of the traditional Euclidean distance, to have some data-driven distance which provides more meaningful information in order to determine whether one block should concur in the denoising process of another block. And in this domain, you can find like deep learning techniques for estimating distance, or most other data-driven techniques, not only deep learning models like isolation kernels, which is from the anomaly detection literature, which I will talk at the end of the slides. And another domain where we can use these models for estimating in distance, say let's call them metric learning models, is in a collaboration we have with a company which is called 𝗙𝗢𝗙𝗀𝗧, where we want to identify users. So these guys are doing authentication systems and on websites like running home banking or electronic commerce to make sure that the user they actually verify the user and to check whether there is no malicious activity on the computer where a transaction is being executed. Here, what we want to use these models is to determine whether for mouse movements or for keystroke dynamics, the user can be authenticated and verified depending on his behavior. Don't have much time to go through these class activation maps. You can find them over the slides. It's another deep learning work we have been doing in the past, which we need some effort to improve it further. And then in computer vision, actually we got interested in template detection mainly. And here you can see an example of a software which a company developed under supervision, where by taking a picture of a shelf, here is a pharmacy, it can identify all the products there present from a given brand. Now, this is not blind, this is not deep learning, this is deep learning free, I can say. The biggest advantage is that you don't need to train a huge model for each that is able to include each and every product, so such that if you want to include a new product, you don't have to retrain your model. It is based on kind of template matching technique. So the advantage of template matching technique is that you build also a correspondence between the picture and what is a reference template. So you just need a reference template for each product, in this case, like one picture of aspirina. And then you can, these template matching algorithms are able to estimate like dense connections between each template, as you can see in this picture for the 𝗙𝗍𝗄𝗎 case, dense connections between the picture and the portion of the template and the portion of the image containing that. And this, I mean, it's very powerful because you can also analyze small regions, like to spot whether that aspirina box contains 20 or 40 pills, and so on. And this is based on robust fitting techniques in computer vision, which are based on analytical models. Say you can use these techniques in order to fit like straight lines among multiple samples, say possibly noisy corrupted samples. And I mean, these are rather old techniques. And say in order to solve that problem, these techniques are used by fitting homographies. I don't know whether you are familiar with. And I mean, there are two different approaches for robust fit. One is consensus analysis, where you look at models and you choose the models which, like in this case, have many points that are supporting them, say they are nearby them, or they use the preference analysis, which has been in particular proposed by a postdoc of mine, 𝗙𝗢𝗟𝗟𝗢𝗪, who joined my group lately, where you change the perspective and instead of looking at models, you look at points. And you look at each point to which model it refers to, say, which model it prefers. So from here, the name preference, and then you perform clustering according to the preference. So you can see these are kind of embedding where each point is associated to a matrix, to a vector which contains its preference with respect to a bunch of models you can choose in your data. Now, these paradigms are very powerful, but holds only for analytical models, say models of which you have an analytical expression which you can fit like in a closed form to your data, either homographies, lines, circles, fundamental matrices, whatever, from computer vision. Our idea is to extend this paradigm to handle like models that are not necessarily analytical, and these can be models that can fit only your region locally, as in this illustration. You can see that the template, the clock, can fit only locally the picture, or model which has a parametric expression, but are not like analytic in a sense. They are not so simple like straight lines, but are indeed like a neural network. And just to give you an idea of the potential of this, I would like to involve you in this work. In some cases, like again in point clouds, you really would like to fit both. You want really to fit like planes, like geometrical entities and non-geometrical entities, like couch entities that are like easily recognizable from their appearance, and entities that for which you want really to know the analytical expression. And so this is one. The other one concerns the fitting of local models. So here it's required some background in computer vision or in pattern recognition, and of course in deep learning. Now let me. I know I've been rather fast, but I'm running out of time. So let me jump into machine learning for health. And I want just to tell you about this project, which started like 2 years ago, where actually 3 years ago, then we got a PhD student, 𝗙𝗢𝘽𝗎𝗓𝗄, who is actually interdisciplinary PhD student. He is from aerospace department, and he's studying all these. So he's like black belt of computational fluid dynamics, which means all this software that makes simulations of airflows. And with his supervisor, they wanted to study the airflows in the human upper airways, like in our nose, okay, in order to diagnose pathologies. And then this ended up in this PhD grant being sponsored in order to perform CFD simulations into real CT scans of a user. Yeah, you have the simulation here. So there are patients which are provided by, say, Università Statale di Milano, which is also collaborating in this project. And from these patients, you get a 3D reconstruction of the nasal surfaces. And then I'm getting back to this in a while, but the major idea was to run CFD simulation to estimate the airflows along these the nasal surfaces, say the human upper airways, and from these, say, infer what kind of surgery the doctor should perform, like septoplastic or turbinoplastic or whatever. So this is a very interdisciplinary collaboration because, I mean, this is very challenging. Just consider that this kind of one CFD simulation can take hours, and it's around gigabyte of space. And of course, there is a lot of variance depending on the way you choose the point. So you cannot just take this and feed it to a straightforward neural network and hope it will work. You don't have so many data even. So we have been using all these models in order to classify these CFD simulations. We have been performing our feature extraction processes, and we get, say, satisfactory results on kind of toy examples. But the nice part of the story is that it is not just limited to, say, machine learning, which is what I'm interested in, not just the medical aspects and computational fluid dynamic aspects. It ended up also into computer graphics, because with these scans, three-dimensional scans, you got of our nasal cavities. There are plenty of like what I call the sinuses, like these regions, which are not relevant in order to perform the simulations. And these, I mean, either need to be removed manually or through the help of computer graphics. And here we use like functional maps and all these derivatives that are also used to perform data augmentation and introduce deformations into these surfaces to like simulate the effect of disease. And you can see the effect of functional maps, which is, so these are two noses. Here are the nostrils where the airs enter. And you can see that there are like these point-to-point mapping between the two, which are estimated by these functional maps techniques. And of course here, I mean, there are plenty of opportunities. There are already two master science students doing their thesis to to this purpose of performing like classification of the disease, of what kind of surgery to do over this kind of input. And let me just the last, still in 10 minutes, so 5 minutes for mentioning what we are doing, like what is mostly related to data stream analysis, where samples can be considered as random vectors or point drawn from a distribution. And here we have been working in anomaly detection techniques. And if you are interested in this domain, I recommend you to have a look at this isolation forest work, because it's like it's embarrassingly simple and incredibly effective. I mean, in order to detect isolated points, to detect anomalies, you draw a forest of trees that are like built up by random splits. And the criteria, okay, I'm skipping a bit the technicalities, but the idea is that a normal point when crawling this forest will end up typically at the end of at the deeper leaves, while an anomaly will be in the higher, in the shallower leaves. And you can use these just to identify what is normal, what is anomalous, under the principle of the 𝗙𝗎𝗎𝗍 of isolation in order to perform anomaly detection. I mean, this has become a paradigm. I mean, you have like these also recently. You can find this I4 in like scikit-learn implemented, and there are still variants of this model that are building upon this model that are, say, improving. What we did was to perform like anomaly detection in a different scenario where you are not just interested as for I4 domain in order to detect anomalies as a sample that falls in low density regions. So if the greens are the normal, the green samples are the normal, the red one is anomalous because it's, say, in a low density region. What we wanted to do is to design an algorithm able to detect anomalies that are like structures, say, that are not nearby, that do not conform structures describing normal data. So normal data in this case are aligned along two different lines, and what you deem as anomalous is not whether a sample is nearby the other in high or low density regions, like these are kind of in a low density region, but this is normal because it refers to the line. And to this purpose, we have been proposing a modification of the I4, which we called preference isolation forest, PIF, which builds upon what I was mentioning before, that embedding, where each point is seen as a representation of all the models that agrees with him. And in that space, in what is called the preference space, we need to build a different kind of trees in order to perform anomaly detection. And here we are. I mean, we have recently done this work, and now we want to expand it to categorical data or to explore further our ideas on how to solve these anomaly detection problems. And like very related, there are clustering problems, because it turns to be particularly effective is that once you have like your model able to determine what is nearby, what is normal and what is anomalous, you can use the same tree in order to determine whether the points are nearby. And this also connects to the previous ingredients I was mentioning for image denoising, like where you want to estimate whether a patch is nearby to the other. And this can be used for performing clustering, where now clustering can take into account similarity according to local structures, like in this case, in order to clusterize points that are not depending on their density, but rather whether they conform to similar structures. And okay, and we are also been proposing these kind of trees for change detection purposes. And here the primary goal is to address categorical data. One of the challenges we are addressing with a PhD student of mine, Nicolò, recently, in designing adaptation techniques for this kind of models, which we called in this case quantry. Now, let me just like 2 minutes presenting what are the research opportunities in collaboration with companies, and I will just mention those with extreme microelectronics, which are those that are like kind of confirmed and say urgent. Now, these are not like internship you can find in, so these are not internship that a company asking me to promote. I mean, these internships are going to be done in a research team in a STEAM microelectronics, which I'm collaborating with like on a daily basis. Say, if not on a daily basis, say every second day, we have a strict interaction for research purposes. And there are actually 2 PhD students sponsored by them and different master science students. So these are not, you won't go there to work on the copy machines or to do some just minor work, but to work on an engineering project or together with this team, which these 3 guys actually are or have been PhD students in Politecnico di Milano. And in particular, what we are doing with these guys is to monitor the production of wafers. So wafers, silicon wafers, are where these discs made of silicon, where each chip comes from. Like each chip you get in your smartphone, in memories, in sensors, comes from these guys. And they are performing like, and we developed the monitoring tools in order to determine whether some wafer has been contains some defect. I mean, we are not detecting each and every defect on the wafer, but we are instead, this is done by inspection machines from the production. We are rather analyzing these maps where all the defects are reported. And in these cases, so it might be normal to have like to have some defect in silicon wafers. I mean, there is some defects inside, for example, the silicon. But when you have defects like these that follow some pattern, then this indicates that there is some problem in the production, and then you have to stop the production and say fix the problem. Like maybe there is a robot which is moving these wafers that is scratching them. If you consider that it can take weeks sometimes to produce these guys, then I mean it's something you have to act very promptly. And we have actually implemented a suitable deep neural network in order to classify these patterns, and which is currently analyzing a few production lines, in particular here in 𝗙𝗢𝗙𝗢. And now there are many activities to be done next. So it's not just a matter of classifying, it's a matter of keeping this model, say, trained and updated and identify even more and more kind of defects, even the more rare ones. And in this case, so you touch the problem of active learning, where you want to identify which samples you would like the inspector to supervise and give you a feedback, or adaptation techniques, where you want to take a model pre-trained over a certain building facility and move it to another one and detect whether there are like evolution of the, and once you have deployed the model, once you have updated the model, detect whether there are novel classes, say, occurring, say, novel types of defect which you have not encountered before. This is classification in the open set scenario. Or you want to see whether, I mean, there is some problem drifting that makes the production drifting and say, letting the defects kind of increasing or stuff like that. And another problem, again related to distance measures, is the similarity search to retrieve over a huge data set of defect images. So we are not handling these maps, we are handling like defect images to retrieve the closest defect to a query image. And this is also done by metric learning techniques. And also another problem is to remove this kind of defects which appears in these images. You see there is like a white region, and again here this can be addressed by several image processing techniques. Okay, you can find more information. So the stages are now, these stages are done like remotely most of the time, and sometimes you say once or twice a week. Once a week, I don't think more. Okay, then depends on the condition, you have to go there. Okay, that's it. Thank you very much. If you have any question, please. Sorry for taking a minute longer. Are you there? Yes. No questions? Okay.
Okay, Professor. Thank you so much for joining us. It was really, really interesting.
Thank you for the invitation. I think that's a nice initiative. I mean, like good for you to choose the thesis you prefer.
Thank you again.
Okay, so good evening. Thank you very much. Bye.
Bye.